to give a talk in this audience. So as I already started to explain in Russian, so let me repeat this. It's mostly based on a relatively old work of mine of 2016, and is somewhat related to even earlier works with Kostya Alkalaev and myself. And but now there is a ongoing activity which hopefully will appear soon with Alexei Kotov. It's like more general version, but in the case of gauge system in the Batalin-Vilkovisky like framework, so like full-scale BRST extension of this story, which is not straightforward, not entirely straightforward. I'll comment on this. And also there is a work in progress of a student of mine, Slava Gritsayenko, who considered one special system which is interesting in this aspect. Okay, so what it is about? It is motivated by, and I'm a physicist mostly, I'm a mathematical physicist, so my motivation comes mostly from gauge theories and things like this. And in physics, we know that Lagrangians are inevitable somehow. As they are inevitable in quantum field theory, whether you consider path integral quantization or Hamiltonian quantization. To do Hamiltonian for path integral, you do need Lagrangian. For Hamiltonian, you need symplectic structure, which is determined by the Lagrangian in a certain sense. But not only quantization, even at classical level, Lagrangian formalism is very powerful, especially if you are interested in building new models or studying interactions of gauge fields and asking questions like this. But the drawback of Lagrangian formalism is that it is not invariant, because it is defined in terms of jet space, not the equation manifold. We need to specify a certain jet space. Of course, it is defined up to some equivalence. You can always add extra variables or remove certain variables called auxiliary fields, going from one Lagrangian formulation to an equivalent. But one way or another, it's not invariant. In contrast to the notion of just PDE, the notion of variational PDE is not really invariant. And this causes some problems even for physicists who are trying to build Lagrangians for certain models. Mostly what I'm concerned with are so-called frame-like Lagrangians. It's the one like Cartan formalism of gravity, this sort of object. So somehow what we are missing this invariant approach to Lagrangian formalism. And surprisingly, if we are talking about ordinary differential equations, so n equal 1, n is space-time dimension for me, then morally we know the answer. And the answer is the standard Hamiltonian formalism in one and another version, either the constraint dynamics or the presymplectic version of Hamiltonian formalism. And we know once we have a phase space, which is roughly speaking an equation manifold, we have some structures there, including presymplectic structure, and then we build the canonical first order action. In simplest cases, this is a standard Hamiltonian action from which Hamilton equations follow as euler Lagrange equations. And this was observed long ago. I don't know the exact date. It's some beginning of 80s by Marc Annaud, who treated this as an approach to inverse problem of variational calculus to in the case of one dimension or field theory, but where you explicitly separate time and keep track of the rest through as an infinite dimensional manifold. Okay, so in some sense, what I'm trying to talk about is a sort of multidimensional generalization of the construction of Hamiltonian action. It's of course a very tricky subject, this covariant Hamiltonian formalism, because sometimes it is considered as a sick area of research. But here I don't insist on its interpretation as a generalization of Hamiltonian formalism. I'm just interested in Lagrangians of a certain structure, which is reminiscent of first-order Lagrange Hamiltonian action, which we know from textbooks on mechanics. Okay, I know that in this audience, I don't need to explain anything about jet bundles or partial differential equations. You know it's much better than I do, but still I need to fix my conventions, which are very naive. And also, Iosif asked to be more pedagogical, so I think it's worth spending some time on introducing conventions. So the standard, absolutely minimal framework of jet bundles for studying partial differential equations is as follows. So we have a fiber bundle. So base space is a space of independent coordinates, and fiber is a space of dependent coordinates. So configurations of our system are sections of this bundle. So I totally disregard global geometry. It's nevertheless instructive to use language of fiber bundles. Oops, sorry. Okay, and I always use X for space-time coordinates and phi for field coordinates, so dependent coordinates, but sometimes different. So jet bundle is it's a jet bundle of jets of it's a bundle of jets of sections of the initial bundle F, and in coordinates if you consider jets of order k, it contains x, phi, and derivatives up to order k. There are natural projections to 0 jets, which is isomorphic to jet bundle itself. And despite that, we are always working with local objects, so which depend on only finite number of coordinates and hence of derivatives up to finite order. It is convenient to work with infinite jet bundle, but to have in mind that we are working with local system, we restrict to local functions and more general local differential forms. So those which depend on finite amount of coordinates, so more geometrically can be thought of as pullbacks from finite jets to infinite jets. Okay, and there is a structure canonical on the jet bundles called Cartan distribution. It can be interpreted as a flat connection. It gives a horizontal complement of a vertical subspace at each point, and it is generated by total derivatives in standard coordinates. They look like this, and this can be considered as covariant derivative with respect to this flat connection. Strictly speaking, it's probably, one should say, Ehresmann connection, connection in Ehresmann sense, when identifying Cartan distribution as connection. And another point of view, or another definition or property of the, maybe we should ask someone to stop microphone because there are many sounds coming, some annoying. Please check if your microphone is turned on. Okay, so total derivatives. So if we evaluate a local function on a section, prolongation of a section, then it is the same as total derivatives of a local function, and then evaluation gives the same as just a derivative of the evaluation. So it's a defining property of total derivative. Okay, it is convenient to introduce differential forms on the jet bundle. So because there is a decomposition into horizontal and vertical, because there is a Cartan distribution, the algebra, the exterior algebra of, oh, sorry, it's here, should be jets. The exterior algebra of forms on the jet bundle is bigraded. The first degree is horizontal degree, and second is the vertical degree. So horizontal forms are basis differential of horizontal forms are dx, and dv of fiber coordinates are basis differentials of vertical forms, and the de Rham differential splits into the sum of horizontal and vertical paths. Each of them is nilpotent and commute to one another in a graded sense. And of course, it's just a decomposition of de Rham with respect to by degree. Okay, it's a standard material, and sometimes this algebra of forms on this on the jet space is called variational bicomplex. Sometimes one also adds this functional form there, but yeah, we will not be explicitly using them. Okay, so this this geometry of jet bundle gives a natural setup to define what partial differential equation is. So if it's a jet bundle of a fiber bundle, then the partial it's a natural setup for partial differential equation understood as condition on sections of the bundle. And the naive definition is that partial differential equation is just a collection of local functions on a jet bundle, which determine these data determine equation manifold, or physicists call it stationary surface often, which is by definition just a surface determined by constraints E alpha equals 0 and all their total derivatives. This is called infinitely prolonged equation manifold. And it is usually assumed that among equations there are no those on the which restrict the independent variables, so that stationary surface itself is a bundle over space-time. So the projection is surjective. The projection of from equation to the base, to the space-time, is surjective. By construction, the total derivatives, they are tangent to the equation manifold, so they determine Cartan distribution there. They determine decomposition of forms into horizontal and vertical pieces, and this gives the variational bicomplex of the on the equation manifold. Okay. Well, actually, I already said this. One can think of the horizontal differential. It's a useful point of view. One can think of DH as an object which generates the Cartan distribution, especially if you promote, if you think of basis differentials pulled back to the entire jet space or entire equation manifold as Grassmann odd coordinates, then DH is just a odd nilpotent vector field, and we know that odd nilpotent vector fields of degree 1, they typically generate certain distributions. So this DH is precisely the odd nilpotent vector field which generate Cartan distribution. Okay.
That's one question, Maxim.
Yep.
You consider equations independent. You consider equations independent, or there are connections between them? I'm sorry, just to double check your notation.
What does it mean? Independent?
Equations. You can the number of equations is equal. Okay, I don't want to say mathematically wrong things. You consider equations they're related with symmetries or no?
For the moment, I assume nothing. I just have a surface.
Sorry. Just okay. Sorry.
Okay, and so studying the geometry of this equation manifold suggests the definition of the intrinsic definition of partial differential equation, which is simplified version of what Vinogradov proposed long ago. Of course, Vinogradov's definition is even more general, but here I'm not trying to be general, so I really consider just bundles over space-time, over independent variables. So according to Vinogradov, PDE can be defined as a bundle over space-time. You can forget about the jet space for the moment. And the structure which knows about the equation is this Cartan distribution, which is involutive distribution on the which projects to the base, to the tangent space of a base, which is specified on this bundle. And it turns out that one can reconstruct everything starting from this data, irrespective of which jet bundle you started with. Of course, there are difficulties because all these are infinite dimensional manifolds, and in principle, if you consider something just with that, you can end up with some quite wild beast, which contains, for instance, infinite amount of derivatives, somewhat non-local or whatever. So there should be extra conditions. But and these are difficult issues, but I'm not going to address them. Somehow I always assume that in principle, one can always embed the PDEs we are interested in into some good, nice jet spaces at the end of the day. It's a subtle point, but it's not what I am after in this talk. Okay, and I'll use notation for the PDE in this sense as a EX-DH, where EX is a fiber bundle over independent variables X, and DH is a horizontal differential. So if I consider horizontal forms on this guy, so I have an important differential there, which encodes for me Cartan distribution. This convention is convenient, especially when you want to extend these notions to gauge systems using supergeometry. And the advantage of this Vinogradov approach to PDEs is that it is sort of invariant. For instance, it's very easy to see when two PDEs are isomorphic, because these are just isomorphic bundles which send and respective DH differentials are mapped to one another by amorphism. They are mapped to one another by the isomorphism. Okay, so let me give a very stupid example. Typically, I give it when I talk to physicists, because they like the simplest example of field theory, which is a scalar field. So let's consider the scalar field with such Lagrangian. So it's just usual second order equations. So equations of motion are like box phi equals to dv over d phi. As coordinates on the stationary surface on the equation manifold, one can take all traceless pieces of all derivatives over phi. Traceless because equation is imposed, so traces can be removed by using equations of motion. So on the stationary surface, traceless parts of phi can be considered as independent coordinates. And the horizontal differential look like this, the first terms. So the first equation simply tells us that Cartan distribution projects to tangent space to a base, or in super geometrical terms, that DH projects to the RAM on the DH differential projects to the RAM differential on the base. And then we have some formulas. So the first formula is unchanged, just like on jet space, but in the next formula, we already started to work in intrinsic coordinates on the stationary surface, and we see that DH becomes tricky. In particular, it starts to depend on the potential, on the V in the beginning, so it knows about the equation. So if the system, for instance, is nonlinear, so V is cubic or high order in phi, then this DH is also nonlinear, and it knows about the equation. This is in components, like explanation to physicists of how to reconstruct how the information about the nonlinear partial differential equation is encoded in this horizontal differential defined on the equation manifold. Okay, so let's see how to extract this information. So the standard definition is that one can define actually solutions to the equations, to the partial differential equation, just in intrinsic terms. So by definition, solution is a section of the equation. Recall that it is a fiber bundle over X, and the solution is a section which is parallel with respect to Cartan distribution. So that's this formula. So if sigma star is a pullback, just reads like this. Or if we introduce the coefficients of the Riemann connection, it explicitly takes the form of covariant constancy equation, where gamma are coefficients of the Riemann connection of the Cartan distribution seen as a Riemann connection. And in fact, these physicists are also interested in such a representation of this like covariant constancy representation of PDE, and it is known in field theory under the name of unfolded formulation. It's strictly speaking not this, but closely related. There are some subtleties, but morally it's towards this direction. Okay, so what we have, let's summarize this point, that what we have is that we are able to embed our equation into a certain jet space which is constructed out of the equation itself, because this equation precisely, this guy with a star, is precisely the one which tells us that this equation is just a usual partial differential equations in terms of dependent variables psi's. But psi's are precisely, oh, sorry, they should be small. Well, identify, they're in the same equivalence class. Small psi and capital psi, roughly speaking. It's just a typo. So we constructed a jet space, which is a jet space of the equation manifold itself. Because it's a bundle, there is an associated jet space. So this equation gives an embedding of our equation into a certain jet space, which is just first jets of the equation itself. In general, of course, this equation, this fiber bundle EX is infinite dimensional, but it should not be a big problem because, strictly speaking, everything, all non-trivial parts, sits in the finite dimensional. In the finite dimensional piece of EX. So you should not be really afraid of working with partial differential equation with infinite amount of dependent variables. And as I'm going to show, once we go to Lagrangian formalism, indeed we will construct a Lagrangian on this bundle, which is a true local function. So it really depends on only finite amount of coordinates. Okay, so let's go to Lagrangian equations. So the standard understanding of what it is as follows. Suppose we have a jet bundle and a system of partial differential equations. This system is called variational. It's the most stupid definition you can give. It is variational if these local functions EI are just Lagrange derivatives of a certain local function L, which is called Lagrangian. So this guy. So this is a standard, like basic textbook understanding of what are Lagrangian equations. And in what follows, I'm going to work mostly in terms of Lagrangian form, which is a top form. Recall that n is a dimension of my space-time independent variables. And I use the following conventions for the top form and this guy, and for co-dimension 1, co-rank 1 form. This is like this, and epsilon is a totally antisymmetric symbol. So strictly speaking, these formulas are not coordinate independent, but the proper language is entirely in terms of differential forms, and Lagrangian is a maximal rank form. So once you do everything in terms of form, you restore the coordinate invariance. But here with my examples and some of my formulas, I'm trying to be maximally naive and explicit to give you a feeling of what's going on, so I don't bother with using a genuine geometrical framework, but there is no problem to do it. There are no limitations in this aspect, in this respect. Okay. So what is important that, as I already said in the introduction, that notion of Lagrangian is explicitly based, or on variational equations, explicitly based on the realization of the equation in terms of a jet bundle. For instance, it may happen that we have a equation and it is variational if we embed it into one jet bundle, and it is not variational if we embed it into another jet bundle. But as partial differential equations, just the same equation, just to realize differently. These are two different realizations. And Lagrangian contains almost no invariant information about the equation, because the only natural thing you can do is to restrict Lagrangian to the equation manifold. And this, of course, it's an interesting object, but quite often it is just zero for non-trivial systems. So clearly it does not carry full information about the Lagrangian formulation. So before studying the geometry underlying Lagrangian formulation, let us try to give a more geometrical definition of, more invariant definition of what it's natural to call variational or Lagrangian PDE. So if we are given with a PDE in invariant terms, so irrespective of the embedding, it is natural to call it variational if there is a bundle and n form on the top form on the respective jet bundle, the Lagrangian form, such that the equation manifold determined by Lagrange equation derived from L is isomorphic to the initial one. So if we can succeed to, so we would call equation variational if we in principle we can embed it into some jet bundle, and in such a way that they derive from a Lagrangian. So strictly, so this equation is the infinite prolongation of Lagrange equation of a certain Lagrangian. Okay, so let's see what else does Lagrangian define on the equation manifold. And it is well known. I don't know history well enough. For sure, this was known. Maybe you should correct me. This was known for a long time to people working in the theory of PDE. But in physics community, the attention to this thing was brought by Krinkovich and Witten here. And here also mentioned some works when people try to apply this to search of Lagrangian, to apply this object, this presymplectic structure to this to studying the inverse problem of variational calculus. So the construction is very easy. So suppose we are given with a Lagrangian, then take its vertical differential and decompose it into the piece which is proportional to early Lagrange equations, which are EI just delta Euler Lagrange of L over d phi I, and the total derivative, which in terms of form look like this. It's obvious. So you just extract total derivative and combine terms to get Euler Lagrange equations. And this chi with hat is called presymplectic potential. It is defined on jet space. There is, of course, a huge ambiguity in this chi hat, But what you can do, you can pull it back to the equation manifold and take a vertical differential of it. So you arrive at, well, strictly speaking, it is n-1, 2 form. It's not correct what is written here. I mean here. So it is two times vertical form and n-1 horizontal. So in general, it's a multiform, of course, and it is defined on the equation manifold, and it is called canonical presymplectic structure because it is induced solely by the Lagrangian. And
Maxim, I'm sorry. What do you call conserved form?
Oh, just DH.
Okay. Okay.
So everything is written as just a term. Yeah, it is this equation. Of course, there is an ambiguity in this omega, and it is given by adding terms of the following form, so which are dv and dh exact. So strictly speaking, this presymplectic structure is in equivalence class like this with respect to this equivalence relation. This is absolutely standard considerations. Okay, so let me give an example. Again, it's a scalar field, well, not scalar field, but just some Lagrangian, depending on up to second derivatives. Then it's easy to find the chi explicitly on jet space. Yeah, this should not be here because it is on jet space, and then you pull back. But to write explicitly pull back, you need to introduce coordinates on the stationary surface, and this already depends on what is your equation. So I only wrote it for a very simple example, which I already had, this scalar field with this Lagrangian. In this case, we know that first derivatives are unconstrained. So as coordinates on the stationary surface, you can take x, phi, and phi a. Starting from phi a, b, there are constraints. For instance, you need to take them traceless. But fortunately, these higher guys, they do not enter. The chi is independent of them. So you can even write it explicitly, irrespective of how higher coordinates are introduced. Here, if phi a is just a pullback of standard jet coordinate to the stationary surface, and the same for phi, then you can write chi explicitly. So you don't really have this dependence on higher jets here. Okay, and omega also, you can write it explicitly. As you can see, these are very simple objects. And if you take dimension to 1, you see here there is n-1. So suppose we are in mechanics. So this is something like nonlinear harmonic oscillator. Then this omega is, of course, just dv phi. Again, there is no index because there is only time, dv phi 1. Let me call it this dv phi, which is just dp dq of Hamiltonian formalism. So for ordinary differential equations, all this reduces to standard Hamiltonian story. Because n equals 1, then this form is just 2 form, and it sits on the stationary surface, which is roughly speaking phase space. Well, better talk about contact manifold, but it's already technical details how to formulate it nicely. So so in this way you can invariantly recover the Hamiltonian formalism if you want, but no one guarantees you, of course, that this form is going to be non-degenerate even in mechanics, because, for instance, for constraint system, if there are gauge symmetries, there is a kernel of this. This 2 form has a kernel, and this kernel precisely corresponds to gauge directions. The kernel of this form is a gauge gauge distribution. That's why first-class constraint system in presymplectic formalism look like just presymplectic. It's like Hamiltonian formalism, but with degenerate symplectic structure. It's alternative to the Dirac Hamiltonian formalism with constraints. Okay, but now we are after multidimensional case, so we keep n generic. And as I already said, in mechanics, for n equal 1, the problem is essentially solved just by these Hamiltonian formalism constructions. We can essentially describe possible Lagrangian systems just by studying presymplectic structures on the phase spaces and then writing Hamiltonian-like action. Okay, so let's now forget about Lagrangian. So let's study more general object. So we say that if we are given with a PDE in intrinsic terms, we call, well, again, it's not good, 2 form of degree n minus 1. Yeah, so what I mean, it's because I used slightly different language at some stage, n minus 2 form. So which means n minus 1 horizontal and 2 vertical.
I'm sorry, what do you mean degree when you say degree, Maxim?
There are 2 degrees. The variational bicomplex is degraded. So there is horizontal form degree and vertical form degree. So this form is precisely of by degree n minus 1, 2. So n minus 1 horizontal and 2 vertical. So it is this dx a1 dx a n minus 1. And then you have something like d phi a, this guy. So 2 vertical differentials and n minus 1 horizontal differentials, if you write it in terms of components. Okay, such a form is called compatible presymplectic structure if it is closed and conserved. Conserved means dh closed. Of course, from here, it follows that dv omega is also 0. Okay, and we can introduce the notion of partial differential equation equipped with such a compatible presymplectic structure and call it presymplectic PDE. So it's a triple. The bundle over X, the connection there, which is DDH, the Cartan distribution there encoded in DH, and the compatible presymplectic structure. So where omega, strictly speaking, is better like this, n minus 1, 2 of EX. So this guy. So from now on, until I get to some examples, I just consider some presymplectic PDE. It's not important for me whether this omega comes from the genuine Lagrangian or it is just some symplectic structure specified on the equation. Okay. So given such a presymplectic structure, it determines a map from analogous to the one of Noether's theorem. It determines a map from symmetries to conservation laws. And it works like this. So if there is a symmetry which is compatible with presymplectic structure, so it means that the vector field W, which is evolutionary, so commutes with dH. So let me recall, in invariant terms, a symmetry of PDE is an evolutionary vector field on PDE. Evolutionary means commuting with dH. So it's, if symmetry is compatible with presymplectic structure, we can call it variational, then it should preserve the equivalence class of presymplectic structure. It's not necessarily 0 in the right-hand side of this equation, but the equivalence class should be preserved. Okay, so once we have such a symmetry and presymplectic structure, one can define through these equations, one can define an object of a horizontal form of degree n minus 1, this kW, through this equation, which is conserved, so dH closed. And this is a conservation law, because conservation laws are cohomology in horizontal forms in degree, DH cohomology in horizontal forms in degree n-1. So indeed, you can produce such a KW starting with W. It's easy to check that it is possible to find such a guy by solving this equation. In the case of usual Lagrangian system, this would be just a usual map determined by first Noether theorem from symmetries to conservation laws. Okay. Now, the question which people considered, mostly these people mentioned on this page, is that if we have a presymplectic structure defined on the equation, and the equation is embedded into some jet space, can one try, how can one lift this omega to the jet space in order to determine a Lagrangian from which one hopes to derive the initial equation. And it can be proved that the lift is possible, but the result depends on everything. And in general, you do not reproduce the initial equation. So it's like a weaker Lagrangian, the one you get. So you have a bigger equation. If I understand correctly the history of the subject, this was addressed first by Igor Khavkin, then also studied by, I should mention, Alexei Sharapov, and recently we heard a talk with some more precise statements about this lift by Konstantin Drushkov here. Okay, but this is not what I'm going to do. Well, it's something similar, but still different. So now I get to the construction, which is actually the core of my talk. So what I'm trying to do, I'm trying to determine some natural Lagrangian, which is similar to the Hamiltonian action and Hamiltonian formalism. So how the procedure goes? So I start with a presymplectic PDE like this. So PDE defined in intrinsic terms and with a compatible presymplectic structure on it. So let's do the following. First of all, omega is a closed form. So locally, and all my considerations are local, it can be expressed as a theorem of something using usual Poincare lemma. But this something we then decompose with respect to B degree. One can show that there should be two guys there. First is chi, which is n-1 form, here. And second is L, which is n0 form. So here, D is a total theorem differential on the equation. Just as it's a manifold, on manifold we have a canonical theorem differential. Omega is closed with respect to total differentials, and locally it is exact. And we using Poincare lemma, we find this guy chi plus L and decompose it with respect to B degree of the variational B complex. So there are two pieces, chi and L. And in fact, this chi is of course precisely the presymplectic potential, which we would get if we started with genuine Lagrangian, but now we just recover it as a potential for omega, but in the sense of vertical forms. Okay, and it's easy to see that these equations.
Quick question. So when you construct this potential chi plus L, why do you stop at two terms? I mean, it could have other terms as long as the total degree is n, right?
In general, let me think. In general, especially if you go to gauge system, of course, you have everything. That's true. But here, if I remember correctly, you can stop just here.
So for some equations, you can just stop and you consider those.
Let me. I think it's correct statement that you you can assume that this guy is just like that, but maybe I'll have a look, and I consider.
As far as I understand, you start with a 2 form, and at each step you decrease the form degree by 1. So you start with a 2 form in horizontal direction, right? Then you get 1 form high, presymplectic potential, then you get your on-shell Lagrangian L, which is 0 form, and that's it.
Yes.
You can't
Yes.
produce a form of vertical degree -1.
Yeah, you are right. Yes. That's the argument. Yes. But anyway, here, so you just look for chi plus L in this form. Then the first equation you solve just by Poincaré lemma of a vertical differential. Then in the second you solve with respect to L again using the same lemma, because if you go with dv you get 0, so it should be, the L should exist, and then you just check that L satisfies this just because it's a maximal form. So you solve this descent equation. Okay, and if omega is indeed comes from a Lagrangian, then one can choose this L to be just an initial Lagrangian restricted to the equation manifold. Okay, now we do the following trick. We consider the special jet space, which we already discussed, the jet space of the equation itself. Equation is a bundle, is a fiber bundle over X, and we consider its jets. Then you do the following thing. You pull back this form chi plus L, because now it's a form on 0 jets of this new jet bundle. You pull it back, and then you take a horizontal piece of it, but horizontal with respect to canonical Cartan distribution on the new jet bundle. You already forgot somehow about the initial Cartan distribution which you had on the equation manifold, but now you constructed a new jet bundle together with a canonical Cartan distribution. So you can, any form you can decompose into horizontal and vertical pieces. So you just apply this horizontalization map. You get a
Maxim, I'm sorry, but just to understand it clearly, this J infinity of E, yes? So you can see these are jets of functions on E infinity, yes?
Oh, jets of sections of E.
Jets of sections with the same base that, yes. So you consider E as a bundle and consider its jets.
Exactly, okay. Exactly. And there is on jets we have canonical Cartan, so we just we take form chi plus L on zeros jets, pull it back to all, and take horizontal piece.
So
of course, L
H big is a horizontal part.
Yes.
Yeah.
Yes.
Okay. Thanks a lot.
So L is horizontal. It's top form, so nothing changes to L, but chi produces something. I'll give a coordinate expressions. In fact, one should not use. There is no need to use infinite, because it's easy to see that it actually sits on first jets. So it's enough to just consider first jets of the equation. But just for to intermediate step, you can think of infinite jets. And moreover, this intrinsic Lagrangian is a local function. Even though we have infinite dimensional bundle and jet space of this bundle and jet bundle associated to this bundle, still this LC, this intrinsic Lagrangian, is just a local function, because all ingredients are local. Because this presymplectic structure somehow has a constant rank, so it's only finite amount of coordinates are involved. In fact, that's I wanted to stress the structure of this Lagrangian in terms of components. So if you work in terms of components, it's more clear that what it has to do with Hamiltonian action. So, and it is also convenient to simplify life to think of basis the RAM differentials of the base space coordinates as just odd. So horizontal forms are functions. So all forms are vertical. And then, so what you do for you, GDEq becomes a homological vector field on this manifold. So forms are only vertical forms now. And then you construct Hamiltonian as a Hamiltonian of this vector field with respect to this two form as a symplectic structure. So and then you write so that's what H look like in components if psi a's are coordinates on Ex vertical coordinates. So if you have x, a, psi a, these are coordinates on the equation manifold. And again, in the simple example, that's what it looks like. Here I'm talking again about this Lagrangian, which depends only on first order coordinates and canonical presymplectic structure. Then it's easy to compute chi, easy to compute H. You see it's indeed looks a bit like Hamiltonian. And if you go to one dimension, it is Hamiltonian. Otherwise, it's sort of covariant Hamiltonian. And the action has the following structure. So it's first order. It's of Hamiltonian. It's of Hamiltonian type, but it's multidimensional. So that's what it looks like. So H plays the role of Hamiltonian, and chi plays the role of symplectic potential. But now everything is multidimensional. Actions of this structure are known as multisymplectic in the literature. People did consider actions of this type, but in fact the way we arrived at this construction comes from gauge theories. It's also a particular case of what's called the AKZ action, but it's presymplectic version. Strictly speaking, AKZ action is the one where this omega, if omega were non-degenerate, then it would be really AKZ action. And from component form, it's easy to see what equations of motion look like. So they look like this omega multiply, these are consequences because you multiply it by matrix omega, the original equations of motion. These are your equations of motion written in this intrinsic form. In these first jets of the equation itself, it's a covariant constancy condition, roughly speaking. So it's clear from here that that Lagrangian we constructed produces consequences of the original equation. But it's a bit more trickier than appears because, in fact, as we see in examples, this Lagrangian does not depend on most of the fields. And those on which it does not depend at all, those which sit in the kernel of omega, should be disregarded. Actually, if you do concrete computations, you see that just this guy doesn't depend on them and you forget about it. But to make the procedure geometrical, you really need to take a quotient with respect to regular kernel of this omega AB. Okay, I will discuss in some more details this later. So it's about interpretation of this Lagrangian. And let me get to some examples which are quite, in fact, familiar. So if we take scalar field, which I already used as an example, compute everything, we end up with the following Lagrangian, which is a standard, well-known Schwinger form of classical. It's a like simplest, nicest first-order form of the scalar field. So it has this structure, and phi a is originates precisely from jet space, from first derivative of the initial phi pulled back to the equation manifold. Okay, so in this case, everything is completely straightforward. So let's consider something less trivial. Let's consider higher order system. For instance, take a fourth order Lagrangian, which is sometimes called polywave equation. For instance, box phi times box phi. Compute this chi, compute Hamiltonian, and that's what intrinsic action look like. What is interesting here, that through degeneracy of this presymplectic structure on the equation manifold, the action depends on quite a special set of coordinates on the station, on the equation manifold. And this set is precisely such that it allows to formulate as a first order action the Lagrangian, and it's easy to check that indeed this action is equivalent through elimination of auxiliary fields to the initial one. Actually, this is almost the final point of the proof. I'm afraid I don't have much time for details of examples. You can play exactly the same game, for instance, for Young-Mills theory, and arrive at also well-known first order action for Young-Mills, which has the following structure, and where FAB is not a curvature of A, but an independent field. So this action is a functional of A and F. Of course, the same is correct. It also works for electromagnetism. And this also well-known form, first order form of Young-Mills equation. People like Young-Mills action, people like this sort of action. And now we sort of derive it from this geometrical PDE geometry, if you want. Somehow we derived it, not just guessed. Okay, and a bit less trivial example is gravity. So if you start with Einstein gravity and Einstein-Hilbert action, we can find chi, coordinates which are involved on the stationary surface can be identified as x, metric, g mu nu, and Christoffel symbols because they replace first derivatives of metric. High derivatives are unconstrained, but we don't need them. So this is chi. And if we explicitly do this intrinsic action, we get Palatini action, which is a famous first order formulation of gravity, which looks precisely like Einstein-Hilbert action, but the Ricci curvature is substituted here as a functional of Christoffel symbols considered as independent variables. And if you vary with respect to gamma, you precisely get the condition which expresses that gamma is the Levi-Civita Christoffel symbols of Levi-Civita connection. You plug it back and you get Einstein-Hilbert action. So it's just a Palatini form on general relativity. So this procedure seem to give some natural actions from invariant data. Of course, I use coordinates, but in this case, it looks like there are no real difficulties with regularities, though maybe some general theorems are nevertheless difficult to prove. And let me say a few more words about the interpretation of the thing. So realistically, let me recall that's what equations of motion following from intrinsic action look like. And of course, omega in general have zero modes. So one should consider regular zero modes, so such a vector fields which commute and which do not vanish. They give a distribution, so you need to take a quotient with respect to this distribution, and on the quotient you really recover this genuine set of variables. But once it requires probably some further studies, but this procedure. But again, in examples, you do not really see the problem. You simply get rid of variables which these objects do not depend on. That's what it amounts to. And probably it's becoming already too technical to discuss it in more details here. So let me give you a sort of statement which is not really invariant. So let's introduce a notion of natural Lagrangian PDEs. This is not an invariant characterization. These are Lagrangian PDEs such that they can be brought to the first order form of the following structure, like here, such that there are no Stueckelberg gauge symmetries, so which means that it really depends on all the variables which are written. So there are no trivial Euler Lagrange equations. And also that the stationary surface projects on zeros jets. So that it means that there are no differential consequences of 0 degree. So these variables U, the dependent variables, if you restrict them to the equation manifold, they remain independent. That's the condition. Because there are models where this condition is violated. And then the proof is absolutely stupid. You just plug it in and you see that this form is invariant on the passage to the intrinsic Lagrangian. So we have a statement that for natural Lagrangian PDEs, the intrinsic Lagrangian is complete. So indeed, you start with it and you see that the intrinsic Lagrangian produces for you again back your equation. So you really can, for such models, you can encode all information about Lagrangian formalism in the geometry of equation manifold. But the problem is, which is unsolved, is how to characterize this class of natural theories intrinsically in invariant terms, not referring to one or another embedding into jets. And okay, this is already technical and naive. And let me give you the example of PDE which is not natural. In fact, it is very well known to physicists. And this is a theory of massive spin 2, which is almost 100 years old and which is due to Firth and Pauli. So they succeeded to write down a Lagrangian whose equation manifold is precisely this one. So this gives you the correct set of conditions on a reducible spin 2 field massive in Minkowski space. So trace free, divergence free, and the sort of massive Klein-Gordon equation. That's what you need. But phi here is not trace free. So, and the trace free, the last condition, doesn't show up as a Euler-Lagrangian equation. On the contrary, it's a differential consequence of Euler-Lagrange equations of this Lagrangian, and this is differential consequence of zeroth order. And this precisely suggests that the condition is violated, and indeed, you can do it explicitly and show that intrinsic action, intrinsic Lagrangian, if you build it for the starting from this L, is not correct. It is correct, it is perfect, but it is not complete. It does not produce all the equations. Of course, it can be cured by certain extension of putting extra geometrical structures on the equation manifold, but just with the equation manifold and symplectic structure therein, you can't encode all the required equations. You can reconstruct Fitz-Pauli Lagrangian, and our suspicion is that in fact this gives a sort of the analog of constraint system in the covariant Hamiltonian formalism, because there are like extra structures, like in constraint system. It's not just Hamiltonian and that's it, but there are some extra stuff which has to do with these constraints which we see here. This is still work in progress, so I'm afraid I can't say much more on that. Okay, and I'm almost running out of time, so if you give me a few minutes, I can just tell you a few comments about what it looks like in gauge case, if you really go to Batalin-Wilkowski-like extension of these PDEs. Josif may have like 5 minutes more, or it's
yeah,
over?
Sure.
Okay, very good. Thank you very much.
It's
not going to be long story. Well, unfortunately, in fact, because it's not yet developed to such an extent. So, in fact, how does extension to gauge theories go? The proper counterpart, the geometrical counterpart of PDE in the, say, of what's called gauge PDE is nearly the same structure, but you have additional degrees. So you have a Z grading in the game. So it's a bundle over which is more convenient to consider as the bundle over T1x over our space-time extended by differentials dxa seen as independent coordinates, and there is the canonical differential there, which is just the RAM differential functions here, differential forms, and then you can see the bundle, which is Q bundle. So it's a Q manifold such that the projection to the base is a Q map. So it is compatible with this homological vector fields structure. Okay, plus of course, as usually, you have extra conditions to avoid some really wild objects which you don't even know how to interpret. But the basic structures are like this. And you can naturally give a definition of presymplectic extension. So presymplectic, analog of presymplectic PDE. This is just a gauge PDE, which is equipped with a compatible two-form. Now we don't have horizontal, because horizontal forms are just functions for us, and they are taken care by the Gauss degree, which is the Z grading on the object. So we just have a two-form, which is closed, which is vertical form, what is important, and which is invariant with respect to total Q structure. So Q squared equal to 0. In the case of usual PDE, Q is just DH. In fact, so Q, you should think of Q as DH plus some BRST stuff with ghosts. But you don't, in the category of these gauge PDEs, it's very convenient to completely mix them. You don't really see the big difference between Cartan distribution and gauge distribution. They are sitting in the same differential. Okay, and once you have this data, it is known what to do. You do some sort of generalization of what's called a KZ type Lagrangian. And actually, for me, historically, that's how I arrived at this intrinsic action. I first realized that there are these presymplectic AKZ sigma model with some interesting actions which look like frame-like actions for gravity and other theories, and they started to translate it to usual language, just in case of PDE, forgetting about this BRST structure, just started to translate it into the usual language of jet bundles without ghosts, without everything. So the logic of this talk is absolutely, it goes absolutely other way around than the historical logic for me. Okay, and again, general theory is still somehow under construction, but it's already clear what it looks like. But I will only give a simple example of special example, which is just easier to explain. It's where the Q bundle in question is locally trivial. As a Q bundle, it means it's essentially, and if we forget about global geometry, it's just an AKZ sigma model. So our fields are maps from T1x to a certain supermanifold equipped with a Q field, and everywhere there is a degree. The only difference with AKZ is just now we do not require omega to be non-degenerate, as in the original AKZ treatment. But the expression for action is unchanged. You just, if you are given with a map from source to target, or section if you prefer to speak in terms of bundle, then you can write an action entirely in terms of the base space de Rham differential, in terms of symplectic potential chi in the target space for this presymplectic structure, and the Hamiltonian, which you obtain as a Hamiltonian for the total for the homological vector field Q in the target space. And that's what it looks like in components. It's absolutely invariant and geometrical, beautiful formula. It's just a KZ action, but just in a presymplectic situation. But AKZ actions are known to be topological unless you have infinite amount of fields, so they are not so useful for normal PDEs. But surprisingly, even with finite amount of fields, these guys, like presymplectic AKZ, can be perfectly non-topological. And here is an example, which is gravity. And it also shows the relation between Batalin-Vilkavisky structure. So if we start with BRST treatment of gravity, so we do a jet space not only for metric, but also for gauge parameter, which shows up as ghost. And then we have a total differential, which contains Kazul-Tate and gauge differential. Gauge differential just includes diffeomorphisms, so which act by Lie derivative on metric and also by Lie derivative on parameter. So we can build a KZ form of gravity, but with infinite dimensional target space. But then we can do certain reduction. We can eliminate equivalent reduction. We can eliminate contractible pairs for BRST differential S. Thanks to diffeomorphism invariance, we don't need to really worry about horizontal differential and things like this. I don't have time to explain why, but it's just some simple facts about this formalism. So, and the thing is that finally you eliminate everything. This is equivalent reduction. You stay with diffeomorphism ghost E, which is denoted by E, with its first antisymmetric part of its derivative. The rest are gone. with Weyl tensor constructed out of metrics. The metric is also gone, and covariant, independent covariant derivatives of Weyl tensors, and the reduced Q manifold in the target space looks like this. So it looks like a Chevalier-Eilenberg differential of Poincaré algebra if you think of EA and rho AB as ghosts associated to translations and Lorentz rotations. And then there is a huge part which you can't write explicitly because it's these WR coordinates on the stationary surface of Einstein equations, which is highly nonlinear, but a good so you just know what it looks like structurally, but a good message, good news is that you don't need it for what we need. So we only need these first two pieces of this BRST complex of gravity. And this is sort of minimal BRST complex for gravity theory. It was reinvented by many people under different names, etc. So I don't give exhaustive references here. And okay, now it gives us the example of what is this gauge PDEs in case of gravity. Let's now look for not yet symplectic structures. So let's check that indeed we are dealing with gravity. Consider a section of this, so a map from the source to the target. It is parameterized by fields E, fields rho. Now they become forms because degree must be preserved. So this is of course going to be frame field. This is going to be Lorentz connection. These are some scalar fields needed but all of them are auxiliary. And then we write equations of motion, which are just a parallel condition for the section. And they look like this. So this is precisely the torsion free constraint.
Something is wrong with the sound, I guess.
Okay, now sound.
Well, now it works, but
2 minutes didn't work.
so Maxim, the last 30 seconds were inaudible again.
So what I wanted to say now on this space, it's very easy to guess what presymplectic structure is. You build it out of the only invariant tensor epsilon. You compute Hamiltonian, you write intrinsic action, already BRST version of it, and this is precisely action of Cartan-Weyl. So in contrast to Palatini, which you get if we don't if we don't pay attention to gauge structures, if we do full BV formulation of the same theory, as a minimal action, as an intrinsic action, we arrive at Cartan-Weiler action for general relativity. So I arrived to my conclusions. So indeed, there is a class of Lagrangian systems, which I call natural. Unfortunately, it's not a invariant. There is no invariant and intrinsic characterization of them, for which everything is determined by geometry of the equation manifold, and this can be also done at the level of Batalin-Wilkovitsky formulation. This is, of course, interesting because it helps to develop an invariant theory of Lagrangian systems, but it's work in progress. Interesting that it has deep relation to the familiar first order and more generally frame-like Lagrangians, which people are interested in, at least in field theory. And it has a beautiful underlying supergeometry, that of AKZ sigma models and presymplectic Q bundles. And moreover, in fact, you can relate this presymplectic structure, which lives on the equation manifold. You can relate them explicitly to the graded symplectic structure of Batalin-Wilkovitsky formalism. It was a work by Alexei Sharakov, who showed at least, well, not fully this statement, but at least in certain pieces, he showed how to extract one out of another. And so what we are missing is intrinsic characterization of these natural systems and intrinsic criteria for completeness, non-degeneracy of these compatible structures. So to make sure, to understand if we are dealing with the genuine Lagrangian system, only partial Lagrangian system in invariant terms, without explicitly doing all this extension to jets, these pieces are still missing. So thank you very much, and sorry for taking more time and for the interruption.
Well, thanks a lot.
Maxim, may I ask you a question about gauge symmetry of your presymplectic AKZ sigma model?
Yes.
Part of the gauge symmetries corresponds to the so-called shift gauge symmetries, right? To the kernel
Absolutely.
of the
Yes.
And what about the full gauge symmetry? Do you have some more or less explicit description of this gauge symmetry?
Yeah, again, it's not fully done, but it's not like a full-scale published full theory, but it is clear that you can, and in some particular cases it was written, that you can read off your gauge symmetries out of this Q field of this total differential on the.
We have two sources for gauge symmetries. The gauge symmetries of our initial equations of motion written in terms of this homological vector field Q, right? The standard gauge transformation of these equations. And the other piece is a kernel distribution of your presymplectic structure. So
that's what you mean. Yeah.
What about the full symmetry? Maybe there are some other transformations which we just don't see.
I'm not sure. Okay, so I think the logic I understand is like that. So you first get rid of the kernel of omega, strictly speaking, regular kernel, because it's a bit tricky what kernel is. Once you got rid of this kernel, you end up with some finite dimensional presymplectic AKZ model, for which gauge symmetries can be read off from Q, but it's not just as simple as in usual AKZ, where everything is nice. You have some extra. But at the level of just your equation, your symmetry, or all your symmetries are encoded in Q. If you don't pay attention to omega, then you know your gauge symmetries, of course. But you're asking the right question. I'm just a bit up beyond of what I was telling. Somehow we can discuss it if you want separately.
Okay, thank you.
Okay. Any more questions?
Yeah, may I ask a question? Maxim.
Sure.
So
Igor, right?
Yes, yes. The example that you gave, where the intrinsic Lagrangian is weaker than the original one, that's the Pauli-Fierz model, right? So you mentioned that so the terms that are missing from the intrinsic Lagrangian have to do with this trace-free condition, which is actually obtained as an integrability condition of the original Euler-Lagrange equations, or something like that?
No, not quite. It is related to this. So there are two things. So what you are missing divergence zero equation when you. If you just construct intrinsic for this, this trace is not in your on your stationary surface, right? Because it is zero. You don't see it. But what happens is that the equations of motion derived from intrinsic Lagrangian does not produce you divergence-free condition. Trace-free, it's automatic because it's just your field content.
Okay.
But the divergence, it does not produce. It produces only Klein-Gordon. And you can trace it to the fact that that's why it was a non-trivial task what Fierz-Pauli did. They really introduced this trace as an auxiliary field, which is such that somehow it gives rise to this divergence-free condition, but then it disappears on account of these differential consequences of your Euler-Lagrange equations, giving you a correct station. So you want this stationary surface. You want these three equations: trace zero, divergence zero, Klein-Gordon. And you can't just do it in terms of trace-free field. You need to introduce auxiliaries. That's what Fierz-Pauli did.
So since there are many ways to embed the intrinsic PDE manifold in jets, so if you choose the embedding in a smart way, following, allowing for all these auxiliary fields that Fierz and Pauli introduced. So and you try to obtain the off-shell Lagrangian from the on-shell information, which is the this conserved presymplectic form. If you do these non-invariant things, like if you make sufficient,
if you do, please repeat. It was interruption. Sorry, could you please repeat because it was interruption?
Oh, sorry.
If I start with a Fierz-Pauli, right?
Right. So you start with the intrinsic equation manifold. If you make the right choices about how you embed it in jets, so including introducing these auxiliary fields at the unconstrained level, right? Could you make these choices such that you do recover the correct Lagrangian when you do the extension off shell?
Yeah, but that's what Fierz-Pauli did. They showed showed how to embed in a certain jet space, but it's an art. They guessed how to do it. Okay, what I'm proposing is a machinery, but this machinery doesn't work here. You can even show that you can't find a symplectic structure on this equation, on this Fierz-Pauli equation, such that the associated intrinsic action, this first order canonical action defined by it, produces everything. Just on representation, well, if you insist on Lorentz invariance, you simply see that there are no such structures, something like that. I don't have 100% mathematical proof, but it's more or less, you see that it doesn't go just on tensor structures. So it's really a system of different sorts. It really contains something special, this Lagrangian formulation, and this something special, it has to do with these differential consequences of zero order, which also showed up in the conditions of the statement stating under which conditions the intrinsic Lagrangian is complete one.
Mhm.
So
Well,
I suspect that this is example of Lagrangian PD of special sort. It's something like constraint systems. There should be extra geometrical information plugged in on the stationary surface, which gives you genuine Lagrangian. Maybe I missed something, I don't know. That's work in progress.
okay. No, I find this very interesting because it seems like so these differential consequences they are not part of the intrinsic PD manifold, right? So they depend on how you
That's
embed.
the trick.
So somehow
That's
this ends up visible in the construction of your this intrinsic Lagrangian. Okay, that's just wanted to clarify the situation. Thank you.
Yeah, that's precisely the point. You are right.
Maxim, may I ask you about quantum field theory? Do you see any application of your partial Lagrangian to quantum field theory? Suppose you have some partial Lagrangian. What can you say about quantum theory?
Well, I can always write formal path integral, at least formal,
Well,
with this intrinsic Lagrangian. I can use it for path integral, but I think it should be analogous, so it's sort of dual to what you were doing with Simon, so that some of degrees of freedom are like not quantized. So it looks like it's a Lagrangian, if you want, it's a Lagrangian theory with constraints. So you have with differential constraints, because if they are not differential, you can always add it to your Lagrangian with Lagrange multipliers. But these guys here are like, you have this intrinsic Lagrangian, it doesn't produce you all of the equations of motion, but some of them you keep as differential constraints. And you need to integrate not over all trajectories in your path integral, but only over those which satisfy these extra constraints. That's what it should look like in QFT.
But do you mean you should add some extra equation to somehow reduce your path integral to the stationary surface of extra equation, which
it's a natural construction. Maybe there can be different interpretation. But what it looks
your partial Lagrangian enjoys more gauge symmetry. So when you are working with degenerate presymplectic structures, that means that physical observables, right? They should be invariant under the action of
no. This I agree with you. This which are in the kernel of omega. You should get rid of them, of course. But you should keep your because classically you have PDE, which tells you what is your what are your classical configurations.
Structure just zero.
Yes.
Then all your fields are pure gauge. No physical degrees of freedom. Nothing to quantize.
No, I didn't say that.
But it follows from that. If you have zero action, what then?
Well, okay, you got me. It's okay. I agree. Okay, for what I was saying was somewhat simplified to this, let's say, inverse problem. But indeed, if you are interested in physical interpretation of really partially Lagrangian systems, so those it doesn't give you complete Lagrangian, then in my opinion, of course, these fields which are in the kernel, you still a consistent interpretation, indeed. Right.
You should be gauge fixed, no?
Actually, there are two sources of problem. One is that Lagrangian equations of motion may contain the original one, right? You can start with a box of 5, and your equations of motion, Lagrangian equation, may have a box squared. Right? 5.
Why?
Then
Why?
you can then you can impose some boundary condition with some extra boundary condition. You can restrict your solution space to what you wish, but the rest.
But I don't see. I don't understand the derivatives.
Well, surely equation box 5 equals 0, yeah, is stronger than box squared 5 equals 0, right? So all to the former equation are solution to the latter, right? But not vice versa. And this may happen in your scenario with this partial Lagrangian, when you can get,
yeah, but at least this
equation
intrinsic Lagrangian is always first order. Of course, it is
yeah, they first order,
with
auxiliary fields and so on. When they exclude, we can actually produce high derivative system of this type. And sometimes extra solutions, non-physical solution, by imposing appropriate boundary conditions. That some of you, that your Lagrangian equation may more large gauge symmetry. Okay. They don't. You can just omit some of equation. Lagrangian.
But right? Okay, Alexei, I think you are somehow asking questions to something which I didn't talk about, and indeed maybe I'm not all of it. But again, the full structure in general is your equation manifold, which knows the gauge symmetries and all your equations of motion. It is this equation manifold equipped with Q structure, horizontal differential, not gauge case, or total differential in gauge case. And then you have extra structure, which is symplectic, which determines you this sort of natural. There is a natural construction of this Hamiltonian intrinsic Lagrangian. I probably refrain from giving the recipe of path integral right now. All information is there, and it is clear what to integrate. But I mean, it has to be done and formulated clearly. But it is
not a basic equation solution. I mean,
no, but you need something to integrate integral.
And by partial Lagrangian to quantize it's possible reasonable quantum theory.
No, you need to know how to quantize. It's partial action. It doesn't produce you all equations of this object as a gauge symmetry. It's really mixing two different things. So you have this partial Lagrangian, and you have your equation, and you know what to integrate.
Yes, but you have to fix gauge. You impose gauge fixing condition with gauge out. Yet, but for partial Lagrangian, you have no gauge symmetry, so you restrict your algebra of observables.
No, but there are two different questions. I think we misunderstood the following: that there are these these variables on which this intrinsic Lagrangian does not depend. They give rise to algebraic gauge symmetries which are easy to fix. And there is a genuine gauge symmetry. Suppose we are dealing with, I don't know, Young-Mills. How to gauge fix it. And this is, despite that this formalism is not developed, it's a different issue. And and something really difficult with fixing it is as usual in BV, but something. But if we disregard this genuine gauge symmetry, suppose some system without genuine gauge symmetry, Lagrangian, still like in this math, then still you have an object to integrate in your path interval. So you have the object to integrate, and you have extra differential constants which do not follow from your Lagrangian. So what you do, you integrate with this over the all configurations, satisfying equations which follow from your partial. Seem to give a reasonable proposal. But pretending I have full-scale statements, but in my opinion, it's straightforward. Modular may be some technical.
Okay, thank you.
Okay, I'm not sure I answered this, but we should discuss it probably separately, not to take time of not into this issue.
So again, no sound again.
From me?
No.
Just no more questions.
From no one. So any more?
Well, looks like no.
Can I ask you a question? You hear me? It's okay. Well, let's assume which can be embedded in some jet space such that its presymplectic structure, Euler Lagrange equation, such that its set of solutions coincide with the set of solutions of our initial equation. Let's assume that we have such presymplectic which leads to a set of solutions of our equation after embedding to some jet space. Then I'd like to ask you a question about interesting Lagrangian. Does the Euler Lagrange system of equations for such Lagrangian leads to the equations such that set of their solutions coincide with of initial equation? Then I have to.
Or maybe not, I don't know.
Okay, but there is no horrible sound now.
Now it's okay, yes.
So let me repeat my question again. Let's assume that we have an opportunity to embed our equation to somewhere. Oh, Maxim is lost again.
Yeah, I'm here, I'm following. Yep.
Oh, okay. We have such a presymplectic. We have an opportunity to embed our equation to some jet space, just usual embedding to jet space, such that this presymplectic structure leads to an Euler Lagrange equation, which set of solutions coincide with the set of solutions of our.
Okay.
Does it mean that your intrinsic Lagrangian leads to the Euler Lagrange equations such that coincide with set of solutions of the initial equation?
As far as I understand, and this example of massive spin 2, which Firth and Pauli succeeded to embed into jet space, in a tricky jet space, yeah, this is an example. So there should be a condition, and this I called natural, well, stupid name. It will be gone by some time, but there should be a condition. But I think what is, I take it positively in a sense that systems which are like that, where there should be extra structures living on the equation manifold, Lagrangian formulation. The canonical Lagrangian out of symplectic structure on the equation manifold. If this symplectic structure comes from a genuine Lagrangian and system is natural, this is the condition, then the intrinsic Lagrangian is equivalent to the initial, so it produces all the correct equations. But the crucial point is, I don't know their invariant meaning. There is clearly something there about these differential consequences, but how to see them from the point of view of stationary, from the point of geometry of PD, I don't know. That's an open question.
Okay, thank you.
Welcome. Thank you for the question. It's a correct question, of course. Yep. Now it's from different device. Now I see Igor.
I think we lost all our chairmen.
Okay.
Maybe Misha is still here.
Okay.
Well, any more questions, comments? Well, if there are none, let us thank the speaker one more time.
Okay, so thank you very much.
Thank you.
Okay, thanks. Bye.
Bye. See you next week.
See you.